Welcome to our first hybrid webinar presented by the IET's Anglian Coastal Local Network, which represents members in Norfolk and Suffolk. Welcome to those of you in the local audience here at the atrium at the University of Suffolk, and to folks joining remotely from other parts of the UK and indeed globally. I'm delighted to welcome you all. I'm Kevin Foster. I'm chairman of the Anglian Coastal Local Network, and I'll be your host for this evening. So without further ado, I'm delighted to introduce our speaker, Dr. Felix Ngubia. Felix is a lecturer at the University of Suffolk in network engineering. So nowadays, rail passengers have to come to expect seamless connectivity and multimedia on the move. But the current Ethernet train backbone specification limits the total traffic to about 100 megabits per second. New safety, security, train management control systems, and intelligent on-train sensors will also place additional demands on that information capacity. Felix's talk presents an experimental approach for achieving end-to-end 10 through to 40 gigabits per second throughput over existing conducting media. This is equivalent to 100 megabits per second per user on real-world railway rolling stock. So Felix, over to you.
Thank you, Calvin, for a wonderful introduction. And I want to also use this opportunity to thank the IET for inviting me to give this talk. Without further ado, I'm going to share my slide. I'll quickly give credit to Professor Stuart Walker, head of Access Network Group, University of Essex, UK, Greg Howard, Rail Innovation, UK. Finally, I'll also give credit to LPA Group, UK as well, for their contribution towards construction of the experimental testbed for the 40 gig. Outline of my talk, overview of railway communication, challenging issues and motivation. Why am I really interested in this research? Ethernet train backbone prototype configuration that I'll round up with my concluding remark. Before I proceed, I would like to give you a quick overview of railway industry. Basically, rolling stock has long life cycle, over 20 years. Some goes up to 30 years, depends on maintenance. Safety and security awareness due to harsh railway environment. The railway environment is very harsh. We are talking about the pantograph operating at about 25,000 kilovolts, which is massive. So it's not something that people will just wander around. So safety and security is very, very key. One of the key challenges is that conservative in terms of changes. The railway industry is actually conservative in terms of changes. So adapting to new technology takes time because you have to go through a lot of protocols, validation, standardization, and all this stuff. The last bit is about bottleneck in decision making because most of the infrastructures are owned by government. And once the infrastructures are owned and controlled by government, things normally takes time in terms of procedures to get things approved. Train configuration, which is very, very key, or train composition. Looking at this, we have closed train. Closed train means you have all the train carriages in one consist or one unit. We also have the multiple train unit. So you have multiple of these trains. So you could have 4 cars as a train, then other more cars as well as a unit. So here we have such. Again, we have open trains. Open trains is where the challenge is because if you have an open train, if you are sending message end to end, then definitely within the cars, you need to have intercar jumper. And because you'll be connecting this intercard jumper with channels, to be open communication channel or closed communication channel. There are a lot of issues with open communication channels, which I'm going to discuss about. Even with the closed communication channels, there are also issues. So I'm going to look at all these things in details as we progress. So for us to have end-to-end connection, you need an intercard jumper. So the red arrow there is showing you where you need to have it for you to have end-to-end connectivity. The same is also applicable to the open train. Here you now have the data. You can see the data for the closed train. You don't need any connectivity, so you can send message from one end to the other end, which is, in this case, it could be the driver cab. The same is applicable to the multiple unit train, to the open train as well. So I know I've mentioned about closed and open communication channel. This presentation is all about Ethernet. So I want to go through the evolution of Ethernet over the decade. I know most of us are familiar with some of this, but it's better for me to bring it to the public so that everybody will really understand. We have the standard Ethernet, which was one of the driving factor for us to use Ethernet, twisted pair cable. We have the 10 megabits. So the speed is actually 10 megabits. All Ethernet length, they can support 100 meters. So that is great. We have the fast Ethernet, which is 100 megabits. We have the gigabit Ethernet, which is 1000 megabits. Then moving further, we have the 10 gigabit, which is the 10,000 megabit. Interestingly, 2018, the 40 gigabit was introduced, which was Cat8. So Cat8 can actually support 40 gigabit per second. And the maximum length for Cat8 is actually 30 meters plus or minus 10%. So we are looking at about 33 maximum meters. The challenge with Cat8 is that there is no end connector. It has not been standardized. So the only connector that is available is Simontera, which is actually designed for Cat7. Transmission rate. I also want to show the audience the transmission rate of this Ethernet twisted pair. Here I've highlighted the Cat5e with red. The reason is that if you look at it, we have two Cat5e here. One can reliably support 1000 megabits per second, while the other one with the red can support 100 megabits per second. The reason behind this is that the one using that can support 100 megabits per second uses just two pairs, while the one that can support 1000 megabits uses 4 pairs to achieve that. Again, this is an interesting area for people to watch out for when you want to deploy any category cable, which is twisted pair. The bandwidth, you can see from Cat6, you have 250 megahertz bandwidth. Cat6A, it increases to 500. Cat7, 600. Then Cat7A is 1000. Then if you go further to Cat8, the bandwidth is actually 2000 megahertz. Interestingly, the traditional train, they're actually designed based on industrial field box. The challenge with traditional train is that you have multiple of cables along the train connecting different systems. This actually, introduce a complex network because you cannot remotely manage any of these devices, because the idea is you want to manage these things remotely and also check their state of their health, how they perform, their performance-wise. Interface compatibility is also a challenge. Issue of integrating devices from different vendors is a challenge because they are all equipment are based on proprietary. They are not standardized. So maintenance issue, there will be lots of time wasted, which will also lead to expensive materials to use because everything is based on proprietary. Remote management, as I mentioned, is very complex. The bit rate, as I then was very, very poor. We're looking at about 1 megabit per second. So this is just showing us, the figure here is showing us a cross-section of a standalone solution where you have all the system integrated in the train, connected with different media. So TCN is actually a telecommunication network for standard for the railway. Here we have IEC, which is the International Electrotechnical Commission, which is involved in standardizing most of this stuff. It consists of 2 layers or 2 levels architecture to suit the need of the intercar and the intracar vehicle communication. So the first introduction, it was actually introduced, late 2000, no, early 2000, sorry. And we have 2 layers. One of them is wired train bus, which is 61375-2-1, connecting the vehicles. So if you consider the open train, so you have the intercar jumpers connecting the vehicles. Then we have the multifunctional vehicle bus, which is more or less like your local area network. So those ones are within the consist. So when I talk about consist, so we are looking at each unit of that open train. Consist could be each unit, or a group of units can form a consist in the case of closed train. So basically what that does is that it connects the onboard equipment and devices. So designed for train environment, they're actually designed for train environment and standardized. A clear example of that is what, here you have the train bus, you can see it running. Then this bit here is the intercar jumper. We have 3 of them here. Then within the train bus, you also have the train bus node. So the train bus nodes are actually active devices. They could be switches or routers, depends on the configuration, but most of them are switches. So between the node and your consist network, here you have end devices connected. Great, we've been able to standardize it. Cost has been reduced, but the overall network bandwidth is still very, very low. So how do we improve on this? Tomorrow's train today. So basically how to improve on this, the Ethernet technology was introduced. So based on the Ethernet technology, which follows the same standard, the same architecture as the previous one, which was -1. Here we have 2 layers as well. We have the Ethernet consist network, then we also have the Ethernet train backbone. Secure network for critical train mission were made possible with this because everything is now IP-based. You can now remotely do most of the things you need to do. Modern train have more communication system with higher data rate because with modern train, we have info entertainment, we have passengers counting, we have sensors in the engine rooms, we have sensors on the track, so many things. So all these things contributed to higher data rate. Increase in reliability because we are now relying on IP network. Maximum performance and synergy in terms of hardware and software. So you have things that can work in synergy in terms of hardware and software. No complex network, and the compatibility issue has also been reduced to the barest minimum. An example of Ethernet technology using TCN is clearly shown here. This bit here shows you the consist network, while this other one here showing you where you have the Ethernet train backbone. So these ones are switches between each of these, because from the switch, you can connect to your Ethernet consist network. Great, we have reasonable, satisfactory solution, all good. But do we agree with that? I don't think so, because the current standard for the Ethernet backbone can only support 100 megabits per second. That's total. And when we're talking about peak period, for those of us that live in the UK or developed countries, during peak period, you can have each set of train, we can have up to 1,400 passengers. And that is a lot of data. Going by a recent project that was just conducted recently, Project Swift, which was carried out by RSSB, Cisco, and Network Rail. I think from statistics gathered so far, it was related that over 3 million people used the train within 2 hours, and 33% of them require internet access. So you can now imagine now that we are relying on Internet of Things. You want to communicate, you want to do so many things, or during disaster period, this bandwidth will not be enough to accommodate that. So what do we need to do? Because the life cycle of train is 20 years or more. So we need to now think of how to use existing materials to achieve that. So these are some of the specifications from the physical layer taken from this standard, which is IEC 61375-2-5, representing the Ethernet train backbone. If we are to refer to the Ethernet consist network, we'll be looking at 61375-3-4. Again, clearly, it operates on full duplex, which is mandatory. Physical layer crossover, just one crossover shall be made on line between 2 ports, which is the Ethernet node. Again, you can see here we have Cat5e. So the standard is still Cat5e. That's why when I was trying to give an overview of the rail industry, they are slow to change because of security and safety issues. So comparison of train bus technology. The previous one that was introduced to take care of connectivity was the wire train bus, while the latest one, which is the Ethernet train bus. Looking at this here, you can see that the bandwidth for this is just 1 megabit per second. It's nothing to write home about. If you are looking at 4K CCTVs used by the driver for forward-facing camera. Well, here we now have 100 megabit per second. Hypothetically, we have 1 gigabit per second and 10 gigabit per second. Technically, these things are available, but they've not been standardized. So maximum network length, you have 32 nodes, and they can actually go up to 860 meters, which is great for this. Here we have 63 nodes, 100 meters between the nodes. So these are the standards as well. Challenging issues. What are the challenging issues? We've been talking about low emission zones. We'll be talking about cutting the carbon footprint. So obviously, how do we achieve that? The train will also want to be competing with other mode of transportation. So competition creeping in forms of other mode of transportation. Passengers discontent with existing internet services. Passengers, as usual, want to have connectivity seamlessly, everywhere, always fast. And we know if you travel with the train in the UK corridor, there are a lot of no spots. However, this could be as a result of the train carriage serving as a shield, fire cage, because they are designed in such a way. So even if you have a mobile base station closely located along the train corridor, you still have this issue because of network. So this is a key effect, which we are also looking at from University of Suffolk to see how we can provide a solution to that. We've already had a prototype to that effect, which hopefully presentation will follow soon. Average or no coverage along the UK railway corridor by mobile network operators. Interestingly, if you travel through the railway corridor, it's not only peculiar to the UK railway corridor, it's also applicable to other areas I've been to. The mobile network operators tends to deploy their base stations where they can make more money, return on investment. So the railway corridors are not actually covered. As a result of that, some countries have decided to use dedicated or hybrid. Hybrid means they have satellite. Some use leaky feeder cables within the tunnels or viaduct. Some uses the mobile network operators base station. Lack or inadequate dedicated train to track site infrastructure to support higher data rates. A lot of experiment has gone, a lot of project has been carried out. One of them was carried out, I think one of them started 2016. Their target was to achieve 150 megabits per second, which is project sweeps. As I speak with you today, nothing has been achieved in terms of train to track. And that one currently is going on between First Group and a company in Cambridge. They also claim that they've achieved 1 gigabit per second train to track or train to shore. From experiments and what I've seen so far, this is still under consideration. So why do we need improved Ethernet backbone? Now, the reason why we need improved Ethernet backbone is that after going through all these things, obviously we want to support the train in such a way that they will be able to compete with other mode of transport. And with the introduction of 5G, definitely those passengers on the rail, on the train as well, on board the train, we want to also have the same feelings they have when probably they are in work pass, when they're at home and other places. So the design is to accommodate a suitable retrofit and future-proof Ethernet train backbone in ash rail environment. So the design must be must be able to withstand shock, vibration, moisture, dirt, and so many things. So key priority to train operating companies or ROSCO, that's rolling stock companies as well. Safety of passengers and staff by real-time ultra high definition IP video surveillance on board. If we don't have the right backbone, we're going to run into problem in terms of trying to monitor crime during crime scene or any other unforeseen situation, probably under emergency scenario. I could remember recently what happened when a rail derailed. Probably if we have an 8K camera, forward-facing camera, the driver would have been able to detect some of these things, even if it was a tree in front, would have been able to see it and apply the brake gradually, not getting close. So we need all these things. Onboard info entertainment, high-speed video transmission is also very key. Certifying the fluctuating demand that will enhance the necessary connectivity to realize the internet on board train. So it's not only internet of things. The train also need to have their own internet in terms of sensors, engine temperature. You don't want to look at engine as a whole, the temperature. You want to look at key areas, because key areas of the engines will also have different temperature range, so that the driver could be easily alerted once there is any problem, then he can escalate it to the control room. So it could be as a result of using store and forward. So you store this information and download it once you get to the next station. Problem definition. So the problem definition here, we'll be looking at the intercar communication network in terms of robustness, reliability, low latency. Obviously, once you have higher data rate, latency will reduce. But if you have a lower data rate, definitely you'll be contending with other critical missions. The main requirement of the proposed approach is to minimize crosstalk and electromagnetic interference, including dynamic application. Dynamic application, I'm now talking about how the train is flexing when it's moving. Estimated average data demand for a single train. Looking at this data, it was actually taken from this website, Ofcom. Ofcom has already commissioned people because of the problem, envisaged problem that the UK Railway will face. From 2017, they've looked at a lot of information, and the information here clearly shows that by the time we'll be, by year 2025, we'll be thinking about 3.6 gigabit per second. That's the total. Will this be enough? I think your guess is as good as mine, because I know with the Internet of Things, we now rely, even our phones and so many things, we rely on this. So for those of us in the research area and in the academia, it's better for us to think of the future, not just looking at what we have here, because looking at this data clearly is exponential. It's not something that you say is linear. So this might not really satisfy the need of what is expected. So the method to be deployed to achieve this, different methods of high-speed fault tolerance, intercar jumper communication network has actually been proposed and has been deployed. One of them is optical fiber cable. Great, fantastic, massive bandwidth. Interference due to electromagnetic is more or less nothing. However, how do you deal with the issue of dust when you are changing connectors? This is a clear issue, because what about the flexing? Fiber will break over time. You don't want to go there and be changing this. You also need a reliable technicians, experts to carry out this work. So the whole thing, and what about the water jet, the IP ingress protection? How do you deal with that? So we can't use this within the two cars. I'm not talking about the open train. Wireless communication. Wireless communication is great if you are talking about millimeter wave. But what happened? How do you deal with rain? Because at V-band, we are looking at 60 gigahertz. At E-band, we are looking at 70 gigahertz. At that point, the wavelength is very, very small. Now you are dealing with attenuation due to rain. You are dealing with fog. You are dealing with snow and all sorts of environmental conditions. So this will also be a challenge. We want something that will work with less maintenance. Cost-wise will also be reduced significantly. Optical wireless communication is also under solution. We have the free space, optics, and visible light communication. We know the problem with visible light communication. If you have light from any other source, how do you deal with it? Fog, dirt, free space is also the same thing. So going back to what we've been using and what we are used to, will be the best option will be to use the twisted pair copper cable assembly. So the approach differs from other methods by utilizing the same Cat 5E that is readily available, screen twisted pair. This time around, we are talking about quad because we have 4 wires in it. As the intercar jumper, then the horizontal part within the train, because it's not flexing, it's not moving, we can now use Cat 7, which supports 10 gigabits. An example of cable flexing test was carried out, and I'll just quickly go through, show you a quick video. Here we have different cables mounted on the rig. And what is happening here is that we are trying to simulate the movement of the train within the railway track. And the result to cycle to failure is very obvious here. Considering Cat 6A, using this specification, 24 American wire gauge, which is 0.2 millimeter square, we have the minimum failure, cycle to failure to be 3,250. Then the maximum was this. When we use this equation here, we got 80%, that is massive, is high. We went down and we tried out Cat 5E using 20 American wire gauge, equivalent of 0.5 millimeter. All these things are standardized in IEC. So it's not just being used, they are standardized. And we have difference of cycle to failure of 20%. So this 20%, because of this value, the intercar jumper was chosen using Cat 5E. An example of the Cat 5E is what I'm showing you here. This is the cross-section of the typical 4-wire rail Cat 5E twisted quad cable with 19 conductor strands, whereas the Cat 7 has 7 conductor strands. The difference between this cable and this cable is that each pair of the Cat 7 is further shielded. Obviously, that is clear because it's going to support higher data rates, while this is only supporting 100 megabit per second. So the combination of this and this, we're able to achieve 10 gigabits. One will be wondering if you had to do implement 802.3 AD, which is your Ethernet channel, when you combine two physical logic to form a physical link, to form a logic link, you are expected to achieve 200 megabits. But in this case, you are able to achieve the same 10 gigabits. The technique that was applied was the quadrupole analysis. A lot of physics is involved, so I don't want to bother anybody about that. So in accomplishing the minimal interference within the connectors pins, because one thing is when you want to terminate your cables, for those that are into infrastructure, stripping back length is very, very key. If you want to strip back, you should be looking at about 0.5 inch, which is 1.27 centimeters. If you overstrip back, you're going to miss that twist ratio. And that twist ratio is very, very key to reduce the near-end crosstalk. So it is much that the optimum configuration is similar to electromagnetic quadrupole. So a quadrupole technique does minimize the effect of crosstalk between the pairs in a balanced and symmetrical geometry. So what has actually happened here, instead of having them in pairs, we've changed the configuration. So on the right is like a 2D drawing showing transmit positive, transmit negative. Then we have the receive positive, receive negative here. So this is a MATLAB simulation still showing you the configuration within the pin, how we achieved the configuration within the pin when terminating and to minimize the crosstalk. Once that bit is achieved, the next thing is here we have the two rail Cat 5E intercar jumper because of the flexing that was shown. Obviously, if Cat 7 was used here, you're going to be replacing this often, and you don't want to be doing that because it's not cost effective. So Cat 5E was selected for this point. Then at this point we have, because this part here, there is no movement, so we have rail Cat 7 cable, which supports 10 gig, and the bandwidth is 600. Here we are talking of bandwidth of 100, and we are talking of bandwidth of 100 megahertz. Then the bit rate is also 100 megabit per second. So these are the switches, which was actually developed 2019, because as I said, the rail industry has no Ethernet switch that works at 10 gig. It was 2019. The first one was developed, collaboration with some of us in the academia and a company in Taiwan called Lantech. So this is the configuration using improved connectors here to achieve that as well. 40 gig test bed. So how do we achieve the 40 gig? A lot of further experiment was carried out to see how we achieve 40 gig. So here, which is the intercard jumper, if I go back to the previous slide, here we have two Cat5e. Here, in this case, the number of Cat5e that we have here, though here it has been written 2, but it's actually 8 of them. So 4 times 2 will give you 8 of those Cat5e here. So combining all this and taking them through the Cat7, through the input, the improved connector, connected to the back of this server. So we have 40 gigabit servers here. Since we don't have access to the rail infrastructure, we're able to set up this test bed to carry out the test. So the intercard jumper here is representing 5 meters, while this other bit here is representing 25 meters each. So the total length is 55. Why do we use 25? Because the standard rail carriage takes about 20 to 25 meters. Then the intercard jumper normally is about 1 to 1.5, but we decide to push the boundary to see if we are still going to get. So at 55, we are still able to stream 40 gig across. And the result for this will be shown in my next slide. Before moving further, I would also like to show some of the field tests that was carried out using one of the state-of-art instrument called Fluke Networks Cable Analyzer, DXS 8000, because DXS 8000 can fluke up to 40 gig. However, what we did was to test each section of those 10 gig, and the result clearly shows that they follow the same pattern. The TCL, which is the transfer conversion loss for nest, return loss, and insertion loss, everything passed. You can see the pass status here. Everything was okay, and it was satisfactory. So it means the pass level was beyond the test limit, which is the go, no go. Here is the test limit for your for the nest, and you can see the data points here. Here we are looking at 1 and 2 twisted pair interacting with 3 and 6, and everything is above the test limit. So this point here is the go, no go area. For the return loss, even when we have so many connectors connected, we are still doing very well. Here, the gray area means even if these data points go below this go, no go area, it is not going to have any effect. So performance analysis, after using the Fluke test, we didn't stop there, so we went further to look at by using open source network performance benchmark testing tools, Microsoft NTTC CP. So to validate the robustness of the new experimental approach and to seamlessly support 40 gig link speed over a distance of 55 meters, which I've just mentioned in the previous slide. So length of a passenger car was actually taken, assumed to be 25 meters. So a total of 50 meters was achieved with 2 cars, and the intercar jumper or the interconsist is considered to be 5 meters in this case. Obviously, all these values we've actually extend it beyond the normal value. We just want to see what will happen. These are the results. These are the results that was achieved. Here, this is the total data, which is this value, all in mega. The same thing here. The real time that it took us to simulate and transmit data from one server to the other. Here is on the transmitting side, we have it as 84.69 seconds. Then here we have 86.70 seconds, which is approximately the same thing. We're actually using jumbo frame. The reason why we use jumbo frame is that it's easier for us to run this thing through quick instead of using the standard frame, which is 1,500. Then the total throughput, looking at it again, is similar. The total throughput is similar. However, on the receiving side, there is slight difference, but this is as a result of overhead. So the difference wasn't much. Then the packet sent here, this is an interesting thing. If you look at the packet sent here on the transmitting side and look at the packet sent here, they are similar as well. Looking at this point here, packet received here is the same thing as packets. Packets sent here is the same thing as packets received here. So both ways, we are getting similar scenario. Then again, the retransmission, obviously, retransmission could be as a result of the packet being, if you have packet being moved around and probably the packet was not delivered, what happened is because of the retransmission, we have 22 retransmission. The acceptable level of retransmission should be around 1%. But what we are having here, if you take the ratio of 22 over the packet sent here, you see that there is nothing to write home about. Is way, far less than 0.1. So the summary test result, then in terms of error, there was no error, and we're able to simulate this without error. Series of tests were actually carried out using the field test. We even used the alien crosstalk. The alien crosstalk, we're actually talking about energizing some of this configuration and leaving some out to see if there will be any effect in it. We didn't have any of those effects. So the system actually worked and we achieved the expected results. Summary. In conclusion, we demonstrated the benefit of rail-approved twisted pair copper cable and enhanced connectors assembly for higher data rate in the ash rail environment. The targeted application, which is our Ethernet train backbone communication system with no error, was also achieved. 40 gig data throughput achieved is believed to be the highest reported with this application and offer future proof. Ongoing work, we are now thinking of, we are now looking at extending this method presented here to support something higher than what we've already achieved over the same twisted pair cabling system. Thank you for your time.
Well, thank you very much, Felix. It's a very interesting talk. You covered an awful lot of engineering and the practical aspects there of train communication within the train. It's interesting to note that this is one example where fiber is not the answer. So I take your point about the dirty conditions and the dust on the fibers, and does bring it home that fiber is not the answer for everything. So thank you very much for your presentation. We will now go over to Q&A, and I'll hand over to my colleague George on my left-hand side to manage the Q&A.
Thank you.
Right, so hopefully you can hear me, and the camera might track to me in a second or two. Can I just ask the audience to give me any questions via the Q&A panel at the bottom of the screen, if you have any. Well, we'll start with the ones that we have already. Steve Morton has asked, what is the method of connecting from a train to the public internet? Is that 5G or similar?
Thank you, Steve, for your question. I would say there is no a specific method for connecting to the public internet. Currently, what is obtainable is the train operating companies who have a system where they will have SIM card, and they, use this SIM card the way we use our normal mobile network to connect to the mobile network operators base station. But the challenge with that is that because the railway corridor is not properly covered, so they tend to have a kind of system that has so many SIM cards in it. So with that kind of arrangement, if that equipment has a problem, they also run into a problem because none of these mobile network operators want to take responsibility. So in some areas, you have dedicated trackside equipment where you can use to connect. As I said, when I was giving my presentation, I said there is a project already going on with First Group in Southwestern Railway with a company in Cambridge. I can't remember the name very well. Then there was this project that was also carried out by Network Rail, Rail Safety and Standard Board, Cisco, which is called Project Sweeps. They were also looking at dedicated trackside. In fact, Fluid Mesh was the one that provided the radio aspect of it. Their intention was to achieve 500 megabits per second. But as I speak with you, they could not even achieve 100 megabits per second from the presentation given at Wireless Train 2018. They were still struggling. So I don't know much about that area. But the best way to go about providing seamless connectivity with those on ground, which is train to shore or train to trackside, will be to use an hybrid system. Why do I say an hybrid system? Because if you get into the tunnel or viaduct and you have trackside equipment, obviously the trackside equipment, you might have some challenges. So the best way sometimes is better for you to use leaky feeder cable, which has been used in London Underground. You can also rely on trackside equipment. You can also rely on mobile base station. We are not going to rule out satellite as well in rural areas where mobile base stations are sparsely deployed or during an emergency period. So all these things will give us seamless connectivity. I hope I've answered your question.
Can I ask a supplementary?
Yeah.
You've described an Ethernet train backbone, which will be 40 gigabits.
Yes.
And you described a 1,200 passenger train with 2 megabits per passenger.
Assuming
that. That still requires a continuous Ethernet access of something like 2.5 gigabits, something like that, over 4G, over 5G, over something like that. While the train's moving. Is there a serious project in place to try to resolve that issue? Otherwise, the bottlenecks shifts from in the carriages to the connectivity from train to the rest of the internet.
Yeah, because of the way the train. Thank you for your question, George. Because of the way the train environment is, I think the train communication network, as I explained, has 3 key areas. 2 of them is within the train, which is the train consist network. Then the other one is the backbone within the train. So looking at the introduction of 5G and what is expected, in terms of data rate, it is obviously clear that the train to track side, there is a lot of research going on. The target is there. At least I know of a company who have started looking at achieving 10 gigabits. They've conducted a lot of trials in Russia and other places as well. But everything is still within that experimental state. But once that is achieved, they can now aggregate these things to achieve higher bandwidth. But within the train, we want to see how passengers can enjoy themselves in terms of content delivery, ticket counting and so many things. Crime, if there is any crime, the driver can see it immediately and probably put a call through to the next station so that people will know you can identify using high resolution this thing, like forward-facing camera in the night. The driver can easily detect even a pin because you can zoom in and see things. So without you having all these things on board the train, it will be difficult for you to get this information.
Okay. Thank you for that.
Yeah.
Question from Peter Woodbridge.
Yeah.
Am I correct in assuming that the Ethernet train backbone is used for a whole range of communications? The safety critical, safety related,
Yes.
basic integrity for the
Yep.
onboard train management,
Yep.
but also communications for members of the public.
Yeah.
How are the various categories of traffic prioritized, segregated, and kept cyber secure?
Good, great. The current switches that are just deployed, that I was also part of, that we launched at InnoTrans, has these facilities. So if there is any issue, the critical missions will be given priority, and every other ones will be given less priority. So in terms of security-wise, it's actually difficult because it's not wireless, it's closed. So except someone will wiretap it and cut it physically. And each of these cables are not just exposed, they are passed through tubings and other protection. So security-wise, they are very, very secured. And the backbone is there to serve everything, both the train communication-based management system and every other thing. So it's not limited to passengers, it's not limited to satisfy passengers' level of experience and expectations.
So there'll be a VPN.
Yes, yes.
Category
yes, each category, yep. That's why we are looking at the 40 gigs, so we can dedicate a particular one for specific critical missions.
Okay, thank you. A question from an anonymous attendee. Has there been consideration towards the type of pins used for couplers? Intercar jumpers are often plug and receptacle to support separation of cars for a number of reasons, where the limitation is often in the pin type. Pins for industry are often designed to connect electrical items and not send receive data, is what he says.
Yes, thank you for that question. I will tell you that I have been privileged to work in the industry for 3 years, and I'm, actively involved in this area as well. Most of these cables you see, we carried out in-house tests where we also subject them to different conditions. So the pin is talking about if it is data for the, we have M12. The reason why we are using M12 is that because of shock and vibration. So M12 is one of the things that is used. Then we have the decoded, we have the S-coded connectors. So when it comes to power, we don't use the same pin for data. They are separate pins. So, yeah.
Okay. Question from Dr. B. Did you analyze the observations of Cat 5, 6, 7 cycles to failure normalized by conductor CSA? No scale was in the photos, but the strand counts were different. And did you consider the practicality of more robust Cat 6 and 7 cable types?
Yes, we did. That's why, thank you for your question. Before arriving at this, it took us almost a year to go through all the process of carrying out different rail category cables, and Cat 5 was top of the game in terms of stability for the intercar jumper. A lot of tests was carried out. Unfortunately, I will not be able to show most of them, but a lot of tests was carried out. We did kink tests. A lot of tests was carried out, even injecting high voltage, taking these things to where the high voltage is to see how it's going to react because of the pantograph, the amount of voltage going through. So a lot of tests was carried out, and Cat 5 was the best for that job.
Okay, thank you. A question from Alan Jones. You said that mobile operators were not interested in giving a good service to rail corridors because there was insufficient profit to be made. I understand that there is currently a trackside 2G network for communication with mainly train drivers. Presumably this will be upgraded to 5G, and could this serve both the need to communicate with drivers and to supply passengers with a decent service?
Yeah, based on the, thank you for your question again. I know what you are referring to when you talk about 2G. We are talking of GSM rail, which is just for signaling and for some critical mission. However, the data rate is also very, very small in that regard. Currently, Ofcom has made it a kind of mandatory for passengers to have free Wi-Fi on board train and certain level of acceptable level of internet Wi-Fi on board train. With this in mind, I want to believe that the mobile network operators will up their game and see how they can provide some level of satisfaction to train passengers. So I believe with the advent of 5G, we'll be able to achieve a lot. But that also depends on how quickly we can address the issue of train to shore, knowing fully well that there is issue of Doppler effect and some other stuff as well. Security of these access points along the track will also be given into consideration when you go to the rural area. How do you secure these access points? It's also an issue. So that's why I talked about hybrid scenario.
Okay, question from Carl Spencer. References in the presentation mention mainly UK rail innovations. Are there approaches, developments in other parts of the world along similar lines?
Yes, thank you very much. I've been opportune to attend the wireless train conference in at London on 2 occasions, 2018 and 2019, before the COVID crept in. Most of the operators and most of the captain, that's the rail industry captains, have always been talking about how to improve. Everybody, I think, have different approach of achieving this. However, there is no single solution to that. And as I said, the rail industry is a bit slow to changes. You can see we are still talking of 100 megabits for the total Ethernet backbone. It's because of the safety and security concern. I think with time, most of this will fall in place and other countries will follow suit as well. But I know so many countries are doing a lot to improve the Ethernet facilities on board train.
From Peter Woodbridge, mainly a comment, and he talks about the big challenge for fast train to transfer its communication from one radio base station to the next reliably. Yeah. It seems a dramatically increased challenge to achieve these high data rates and using the public mobile comms infrastructure. He offers you good luck with that, so we'll note that one. And Mark Graves recalls many years ago at university looking at the speed of handoff between different mobile masts for a voice call from a moving car and the amount of handshaking required. Is there a train speed above which data rates fall off due to handover between masts?
Thank you for your question. Currently, to be honest with you, currently I'm not looking at that area so much, and is an area that we in University of Suffolk are going to give due consideration. So I welcome you to send me an email and see how we can partner to, to move this area to the next level.
A question from Andrew Skinner, who's head of engineering at Great Western Railway. He says, great presentation, thank you. And as a traction and rolling stock engineer, I have a concern that the intercar connector data indicates a jumper cable life of only a year or two. Is it intended that they effectively become consumable items requiring regular replacement for the benefit of faster onboard communications?
No, they're not going to be. These intercar jumpers, as I said, some of them are already in place. They are being used already, though they are not standardized. So based on information and statistics available, these intercar jumpers last very long. It's not something that is, replaced over a year, except, I hope I'm answering, yeah.
Yeah, if you could confirm the lifespan.
The lifespan, as far as I know, is close to 5 years. 5 years? Yes, I think so, yeah. If he wants more information, I can put him, I can give him the right contact and to reach, the LPA group. Okay, so Andrew, Felix has indicated that he will put you in touch with the right people to find the answer to that question specifically.
From Kieran Rowley, how quickly can this be introduced to rolling stock? Is it a depth maintenance task or can it be accomplished in normal service timings?
This can be introduced during refurbished, or if you already have this intercar jumper, because I know of so many companies that are looking at it, so it can be introduced during refurbish or during maintenance period. It's not something that is difficult. So you don't require any electronics to do that. It's just changing probably the connectors between the both cars and off you go.
I think we have got to the end of the formal questions. So I'm going to pass one over to the auditorium here to Kevin, who has a question.
Okay, thank you, George. I have one question, and that is, Felix, thinking about power over Ethernet, can this high-speed system support power over Ethernet? Thinking about, powering carriage Wi-Fi access points through this system, or would you need to have separate power conductors for that?
Thank you, Calvin, for your question. The switches and these cables are compatible with power over Ethernet. They can do up to even the latest power over Ethernet, which is, we have class A, which is AF, which supports about 15 or thereabout. I don't have it offhand. Then we have AT, about 25 or thereabout. They can all support, and the switches on board. The good thing about power over Ethernet is that you don't need an additional cable to power your device, mostly your wireless access point. So in terms of, because the more cables you have on the train, the more weight you add on it. So you are trying to avoid that. So power over Ethernet has brought in something very, very interesting, which these cables and the switches are readily available to support.
Thanks, Felix. Thank you.
Yeah, thank you.
Any other questions from the auditorium? If not, I'll pass you over to Kevin.
Okay, well, thanks very much, Felix, for the work you've put into the presentation and answering so many questions. Very, very interesting subject, and I'm sure we could probably talk for hours about it. Fascinating project area, and it brings me back to my own work in telecoms when I did a lot of work on longitudinal conversion, transfer loss, next and FEXT for the broadband access network. So fascinating. So thank you very much indeed for delivering the talk and preparing the slides. Much appreciated. And my thanks to George for grouping the questions and asking them on behalf of the audience. And I'd also like to thank Mark for setting up the auditorium for our first hybrid event. I did note there were one or two questions or comments in the chat field about the camera. We will take those on board for our next one. I know the camera auto zooms to whoever's speaking, so it can pan around quite a bit, and possibly is a little bit annoying. So apologies for that. This is our first hybrid event. There will be some wrinkles. We will iron those out for future hybrid events. So I hope the camera panning wasn't too distracting, and if no, Felix, you delivered a very good presentation.
Thank you very much.
And the slides were viewable. So thank you very much. So I'd also like to remind everyone that we have recorded the webinar. That will be made available in a few weeks' time. Obviously, we're going to do a little bit of post-processing on it to remove any gaps, and we'll do that as soon as possible. So that will be made available on the IET Eng site. So George, would you display the closing slide, please? So we're going to display the closing slide. There's a link on that slide that we're sharing now. That gives you the link to the site where we will have the slides and the recording. And I'd like to draw your attention to our next up and coming webinar, which will be on the 29th of March, and that's machine learning, making smartphones smarter. And that's given by Somdik Day of the University of Essex. So please look out for the registration for that one. That's the 29th of March. The link gives you, on that slide, a link gives you the link to the registration area. So, finally, really on behalf of the IET Angling Coastal Network, my thanks again to Mark and the University of Suffolk for hosting us in the auditorium here for our first hybrid webinar. Thank you to Julie and the team who put on tonight's webinar, George and Ian as well. So that concludes the webinar. You may disconnect now. Thank you very much.